Good day, everyone. Welcome to ME158. And now we will be moving on to discussing Gait Biomechanics. Hello. So I hope you see my pointer. Unfortunately, this is the one lecture that I think should never be done online because I think this is more fun to observe when we are actually together and we're actually capable of demonstrating the motions that we will discuss today. So by this point, supposedly we have discussed inverse kinematics where we understand joint angles, velocities, and accelerations, and how that would influence the required forces for the appendages, like the legs or the hands or the arms, need to do in order to get those angles, those velocities, those accelerations. And the gait biomechanics is kind of like a culmination of that. So when we talk about gait, especially in humans, this is the associated sequence of motions when we're walking and running. So for humans, this is strictly for the legs, although the arms and the rest of the body do play a part in healthy motion. So for humans, we are actually economic walkers. We are optimized towards endurance walking. So like we can essentially walk for hours without getting too tired, and that is actually reflective in the chosen means of life of some of our brethren who are still performing hunter gathering actions in the respective regions. So why should we study gait? So when we study gait, we actually learn what is our baseline for healthy walking or healthy running. So by knowing what is the correct way to move, we learn essentially to detect if there is something wrong with one of our legs or with one of our motions, and we can suggest ways to correct that kind of motion. Also, by knowing how our body moves, we can, of course, simulate walking and running for a variety of purposes. So, our objectives for this lecture is actually quite a lot. Bear with me. So, first, we want to decompose the walking and running gait into several general phases. So, of course, we're engineers. We want to have some bit of order in the chaos that is our movement. We also want to examine the joint angles, the internal torque, the ground reaction forces, basically the inverse dynamics of this entire thing for the walking gait and some of it for the running gait as well. We also want to differentiate walking and running because, well, maybe in your minds, running is kind of like walking on two times or three times speed. They're actually quite different. Now we also want to observe gait changes from that deviate from the healthy cycle. Like for example, those produced by locomotive disorders, and also more importantly, those produced by prosthesis. And as a kind of a foretaste, we also look at general motion patterns and some four-legged animals, mostly two, the horse and the dog. So before we go animal about this, let us go ahead with the human walking gait. So the human walking gait is kind of broken down into seven stages. And these seven stages are broken down in two main phases. The first is the phase where the foot is still on the leg, on the surface or on the floor. So this is the stance phase. So the stance phase begins when your foot makes contact with the floor. So like you move your leg up, and then the moment you touch the floor with your heel or your toe, that is the start of the stance phase. So the stance phase is then followed by what we call the swing phase. So this is the part of the walking where your foot is off the ground. And this happens at toe off. So if your walking is proper, you use your toe to lift your entire leg up from the floor. So that's the stance phase, those, and that is the swing phase. So keep in mind that these phases are really connected to one leg at a time. So when your one your leg, like for example, your right leg is kind of touching the floor, it could be that your left leg is well off the ground, or it could also be touching the floor as well. So this is kind of like an example from another reference. So they kind of classify it differently. So here we have our initial contact. So this person used their heel to make that initial contact. So is that consistent with um, other cultures? Sometimes you actually see initial contact with the toe. That depends. That actually introduces a lot of difference in the dynamics that the body feels. Next is, of course, you have toe off. So this is the moment wherein you push your entire leg off the ground through your toe. So this launches your leg forward, which completes the swing phase. So this is stance phase, and this is the swing phase. Now again, to emphasize, your other leg could be doing a different thing. So in general, or it is usually when you're walking, the right leg, when it is on the ground, in general, the left leg should be in swing. But there are some moments wherein both legs are kind of touching the ground. So we call that the double support. So the double support is kind of like when both of your feet are in contact. So do you actually feel the double support? I suppose it depends on what style of walking you initiate. But yeah, so this is an example of the double support. So both legs are touching. So here, your right leg is at toe off while your left leg initiated contact with the floor. All right. So let's look at the stance phase first. The stance phase actually covers a lot of the entire walking gait. And if we look at our timeline here, the stance is actually longer. So you're when you're walking, usually your foot is on the ground most of the time. So again, this phase is divided into mostly four phases. And these four phases are in total longer than the swing phase. So your stance phase begins with what we call the loading response. The loading response is when your leg, because you're touching the floor already, is starting to bear your body weight. So this starts at initial contact. When we talk about the next phase, this is called the mid stance, which is basically when your limb is kind of in the opposite limb is in swing phase. Basically, okay, so loading response, okay, support the body weight against the floor. And at mid stance, okay, so your other foot is now free to swing. After the mid stance, we have what we call the terminal stance. So the terminal stance begins when part of your foot starts to lift off the ground, and this is usually the heel. So the moment your heel rises, your stance is about to terminate. And of course, the terminal stance will end, or rather, the stance phase ends when your leg is primed to swing forward for the swing phase. So this is the pre-swing. Here, I believe the terminal stance does not really exist in this image. Here we have what we call parts of the mid stance. So these are all mostly mid stance, and here we skip to the pre swing. So the phase in between this image and then that is what we call the terminal stance. So yeah, pre-swing starts when the opposite foot has made contact. So here, yes, the opposite foot has finally made contact and your foot is being primed to spring forward for the swing phase. All right, so now we go to the swing phase. So which is a little less occupies less of the time of your leg during walking, and because of that there are only three phases. So when you swing your leg, it starts with the toe off. So your body propels your leg forward through your toe. So that's why we call it the toe off. It's okay. So after the initial swing, you pushed off the ground using your toe, and then you go into the mid swing, wherein your feet are adjacent. Again, this image uh kind of skips that. If you look at this image, it's kind of more clear. This is the moment when the leg in question and the opposite leg are kind of aligned in this image. So somewhere between this and that, this second and third image. And the terminal swing, it begins when your tibia is kind of positioned to be pressed down. So like for example here in this image, okay, so I swung my foot forward. Now my shin is getting ready to be stamped down onto the ground. So that is when the terminal swing starts. So all in all, this is one cycle of your leg. And if you combine these together, from the stance to the swing, we call that the gait cycle. Or um, in more in more anatomical terms, this is your stride. So the stride is from when your foot touches the ground first, and then when your foot touches the ground again. So that is your stride. There are, aside from this, there are other means of quantifying human gait. So of course you have the stride length, which is the measure of the distance between the footprint of your of one leg or one foot uh and the distance of it to the next one. So that is the stride length. The step length is kind of the distance between two opposite feet. So if this is the right step length, which is the distance from the heel of the left to the right of the left, and the left step length is the opposite, so it's right to left. Now we also have what we call the walking base. So of course, our feet are kind of apart most of the time, and this is something that we should also quantify. Another one is your toe out angle. So when you walk in general, your feet are kind of pointing outwards, supposedly. I am not sure what the implications are if your foot is naturally pointing vertically or forward. Most of the time, I'm not sure what the implication is. Maybe you can ask your doctor about that. So, okay. Another parameter that we use to quantify your gait is what we call the cadence. So, I believe if you're in ROTC or the RIDEA, you're familiar with the cadence. So, this is the number of steps per unit time. So, the larger your cadence, the faster you're walking, essentially. So, now your cycle time is the inverse. So, this is the time it takes for you to complete one cycle of walking. All right. So now that we've done away with the parameters of the gate, now let's look at something a bit more engineering-ish. So we're gonna look at the joint angles in this case. So in this image, this is kind of like a simulated leg. So you have three segments here. You have your uh, you can kind of call it your upper leg. So this is like your femur part of your leg. This one is the shin part of your leg, and then this one is your foot. So you have three rigid bodies interacting with one another. And here, this graph is essentially the joint angles involving these three bodies. So you have the angle for the hip, you have your angle for the knee, and you have the angle for the ankle. So you might ask, okay, so what is zero for a hip angle? What is the zero for a knee angle? So for disclosure, the hip and knee angles kind of have their origin using the proximal segment. So what do you mean by this? So what is the proximal connection of the upper leg? So your upper leg is connected to your abdomen. So the basis of the zero angle is when your upper leg is aligned to your abdomen. So essentially the abdomen is in the same, it's kind of like collinear to your upper leg. So that is the zero mark. For the knee, that is also the case. But this time, the more proximal part is the upper leg. So when we have a knee angle of zero, that means that your upper leg and your lower leg are aligned or collinear with one another. So that is the 0 point. For the foot angle, this is different because it is measured with respect to the ground. So if you have an angle of 0 here, that means your foot is parallel to the ground. So the foot is kind of as a different point of measurement. All right. So okay, look at this. So you have your different kind of stages of walking above here, and it's actually denoted by a line. So you can kind of imagine, okay, so what's the angle of the hip at toe off? And if you look at this, you can kind of also see what your knee and your foot is doing. So, all right, so what's so special about these curves? So these are the curves or the angle function of a healthy walking gait. So what are the markers? So first, so for the hip angle, you'll kind of see that the hip angle is kind of flexed half of the time almost. So it's flexed within the initial swing. So that's when your foot is kind of trying to bring your entire leg forward. So again, if you want to ask, so what's the flex direction for our hip? So the flex direction of your hip is when you bring your femur into your body. So that's essentially bend it upward. That is the flex direction. Extend is when you are trying to straighten your upper leg to your abdomen. So now, okay, so the flex happens within the initial swing and into the mid stance. So there's not much special going on here. So yeah, it's just okay. So it's flexed half of the time. It's extended half of the time. So but the knee angle is kind of interesting because there are two peaks here. You have a peak during the swing, and you kind of expect this because when you are swinging your foot forward, you can kind of sense your shin tucking into your upper leg. I think if you walk faster, that becomes more obvious. So here, your greatest flex is actually within the initial swing, which is kind of here, around here. Now, aside from the swing, there is also some flexion. So flexion is kind of like when you bring your shin backwards. That is the flex for the knee angle. Just in case you're confused. So the greatest flex of the knee happens during the initial swing, and there is another peak, a smaller one, that's happening in the middle of the stance. So it's right around here. So there's this baby peak during the stance, and there's this big peak during the swing. Now, for the foot angle, there's something really special happening here. And it's very clearly happening during toe off. So the greatest plantar flexion again. So plantar flexion is when you bend your foot downwards. So dorsal flexion is when you bend your foot up, plantar flexion downwards. So the greatest plantar flex happens when you're launching your entire leg forward. So this is important. So what does this mean? So in order to have a good walking gait, your hip has to be able to flex, to extend. Your knee has to be able to extend, or rather, it has to be able to flex in two distinct spots. And also, your foot has to be able to bend downward. So these are key things to look out for when you're examining a healthy walking gait. Now, of course, we have the angles. Um, when it comes to inverse dynamics, we are also able to get the internal torque of our joints. Now, this internal torque is kind of imaginary. You have to remember that the muscles are do not act the same way as a robot arm. So these internal torques, I kind of like, okay, kind of summed up. So it's kind of like overall torque that this location is experiencing, but the muscles are experiencing different levels of tension and compression on their own. So take this one in a grade of salt. So right. So the hip torque is kind of like, okay, so there's not much special here. So it's kind of flexed half of the time, extended half of the time. All right. So that's kind of it. Now the foot torque is actually interesting here because if you look at this peak here, this happens during the stance phase. So you can kind of imagine it as like this. So when your foot is on the ground, it is building up a lot of torque in order to take off. So again, during the stance phase, your foot is kind of building that torque just enough to launch the foot forward. And what you notice here is that during the swing phase, your foot is not pressing on anything. It's kind of like just dangling there. So yeah, this is a key thing here. You need your foot to be able to exert torque to launch your foot forwards. All right. So aside from the internal torque, we also have this thing called the ground reaction force. So the inverse dynamics is kind of incomplete unless you kind of figure out, okay, so how is the ground reacting to my foot? And in kind of examining the reaction force of the ground, you notice that the vector of the reaction depends on where your foot is and at what plane is it contacting. You kind of get this kind of heart shape for the overall profile of the ground reaction force. This is kind of weird to think about, but yeah, this is what um, professionals in the medical field have actually discovered. Is that there's this butterfly or rather heart shaped profile to the reaction force, and when you're loading up your foot, you get this kind of peak in reaction force, and then the next peak of the ground reaction force happens at toe off or push off, essentially. So again, the first peak of the reaction force happens when you just load your foot. So this is the first loading or the initial loading, and then the next peak happens when you're pushing your foot or leg off the floor. So if you want to examine it closer, so here is the image of the travel of what we call the center of pressure, or rather the contact of the floor on the foot as you start to walk. And what you notice here is that it's not the contact of the foot against the floor is not on the straight line. It goes from the heel, it goes outside, then goes inside, then leaves your big toe. So again, this is an important marker of a healthy walking gait. And yeah, the adjacent image shows the travel of the COP during a regular walking cycle. So if you think about it, this heart-shaped form is happening while the center of pressure is transferring from the outside of the heel to the inside of the more forward section of your foot. All right. So those are the first examinations of our walking gait. We can also look at the energy that we consume when we're walking, and this is the important part. When we're walking, we are kind of bobbing up and down. So if you take our center of gravity for a human body and you just track it while you're walking, it's kind of like going sinusoidal all over the place. So energy wise, that would mean that our potential energy is kind of cycling in opposition to our kinetic energy levels. So the peak potential of our body occurs in the middle of the stance. That is when our body is at its most raised, essentially, off the ground. And the peak kinetic energy is when your body is kind of at its lowest point and just around toe off. So you're about ready to launch your foot forward. Now there are multiple models for the walking gait. The simplest one is what we call the ballistic model. So it's just using the inverted pendulum as a substitute for the leg. So you can use this method for simplified dynamic analysis of a walking gait. Unfortunately, what you can see here is that there's no flexing knee. So it's just one solid body. So if you want to take it to the next level, you use what we call the dynamic walking model. So you kind of get a knee flexion, and you also get kind of a non-single point contact with the floor. So your leg now has a foot. So this is a little more complicated, but it's closer to the actual thing. And this is kind of a big deal to explore because a lot of people, or rather a lot of research has gone into what we call passive dynamics. Essentially, kind of models of limbs or walking limbs that can passively walk along a descending incline. So essentially, these systems use their own mass or their own potential in order to walk forward. So here are just some examples. So these are what we call passive dynamic walkers. So some of them have knees, some of them don't. And what the neat thing about here is, under the own weight, as long as they are walking on an incline, they are capable of mimicking human walking motion. So here's an example of an engineering project. So you have a passive dynamic walker here, and I believe that some of the applications that are being explored for this is, of course, having um, passive walkers for those who need assistance in walking. So this hasn't quite taken off yet, but there are people who are kind of trying to examine how to make this work for those who have some locomotive disabilities. Of course, another application of this is for walking robots. Of course, these robots do have powered walking systems as well, but if you can design passive dynamic walking into your bipedal robot, you can save a lot of power when you are walking on an incline. So given this, all right, so we've explored the healthy walking gait. Um, what happens when you have locomotive disorders? So we're going to look at two kinds of disorders specifically. The first is the crouch gait. So the yellow graph here is the healthy joint angle of your knee. And what happens here is that when you have the crouch gait, your knee is kind of flexed most of the time. So it's kind of like, okay, so it's flexed in this way most of the time. So you're kind of forced to use your hip to just push your leg forward. So if you look at this graph, the knee angle is in the flex zone most of the time. It kind of makes it hard to walk. You're relying on a lot of hip movement here in this case. The opposite here is that, okay, the opposite is the stiff knee condition, wherein your knees kind of stuck in a particular angle range, and it makes it hard for your leg to swing forward and to prepare for toe off. So it's like you're using your hip to move this kind of stiff leg forward, and that kind of hurts. So yeah, these are the deviations in terms of gait pathologies. Now let's look at the running gait and compare to the walking gait. So this is what our body looks like when we are running. Maybe, or rather, this is what a healthy human running gait looks like. So what you notice here is, okay, this is my stance phase. This is my stance phase. If you look at here, in walking, our stance phase covers most of the face, or over a little more than half. But in running, your foot is in contact with the ground only around 35% of the time. And most of your leg motion is dedicated to the swing. And in fact, if you look here, there is a moment, 50% of your running is actually uh doesn't have any foot on the ground. So we call that the flight period during the stance. This is the moment wherein none of your feet are in contact with the ground. And in fact, if you want to increase your efficiency in running, you want to lessen the contact with the ground and increase the swing phase of your running gait. So now, when it comes to the initial contact or the loading response, there are usually two forms of loading response during running. The first is the heel strike. So this is what most modern runners use, and I believe this is what you use usually when you're running. You lead with your heel, and then you just roll the center of pressure forward to your toe. The other one, the one that's usually used by barefoot runners, is what we call the forefoot strike. They essentially initiate contact with their forward foot pads. So essentially, not essentially your toe, but the forward foot pad of your toe. So there are some advantages to the forefoot strike form. If you look at the ground reaction forces of your running, so sorry, we didn't look at the forefoot and the heel strike model. So we just distinguish walking and running. So with walking, there is an overlap between foot contact. While for running, there is no overlap. Usually, when the one foot is down, the other foot is in swing, and they never usually overlap in period. Now, okay, so let's go to the heel strike and the forefoot strike. When it comes to the heel strike, there are two distinct peaks that are happening. So if you look at this, this is actually the reaction force. Yeah, this is the reaction force. You have two sudden jumps in force when you're doing the heel strike. Well, when you're using the forefoot running method, you have a much more gradual increase in ground reaction force. And this kind of makes it a little healthier for your foot. And that is actually inconclusive with our ancestral running gait. Because before we had very thick soles, we used to run using the forefoot running method. So we essentially led with our toe or our frontal foot pads, and the forefoot running method allows us to engage a lot more of the energy absorbing ligaments and muscle and tendons in our body. So it allows us to carry more of the force into the more flexible parts of our body. Well, in the heel strike, you're kind of forcing the reaction, or at least most of the reaction, along your leg bones. So it's traveling. You can kind of feel when you're heel toe running, and if you run, and if you heel toe run. No, sorry, word salad. So if you heel strike in the wrong way, you can kind of feel it up to your femur. So yeah, that's kind of bad. If you heel strike badly, it will really hurt your hip. But when it comes to the forefoot running method, that force is actually dissipated along your ligaments and your tendons. So your hip and knee won't feel as much of the force. And that is one of those benefits, essentially. So, all right. Yeah, that's a lot of word salad for this part of the lecture. All right, let's move on to, okay, so we've explored disorders. Let's look at the effects of having a prosthesis. So when we say prosthesis, this is kind of like an artificial leg. And there are two types of prosthesis that we want to look at. The first one is the below knee prosthesis. So you've kind of had everything just below the knee amputated. So if you look at this joint angle graph here, you have some of the normal behavior of your hip and your knee preserved. But if you look at your foot angle here, you have a shallower plantar flexion happening. So there is a struggle for those with artificial legs to push off their amputated leg. That's because if you get a very cheap leg prosthesis, most of the time the foot is not articulated. So it's kind of stuck in a particular angle. And you kind of have to modify your knee and hip behavior to compensate for the lack of plantar flexion. So yeah, that's one problem of the below knee replacement. Now, when you replace your leg above the knee, so like there is a knee replacement, most of the knee replacements do have articulation. So you can see here the knee is the false knee or the fake knee is articulating. However, it is not functioning just like your normal knee. So this is just I think this is the profile for a single R joint knee. So it's basically a hinge joint replacing the entire knee. And what you see here is, of course, you do have some flexion during the swing. However, you lose that little peak during the stance. So there's some difficulty here. And you can see in the foot angle, there is some response there. And in the hip also, there is some compensation happening. So what you see here is that the normal hip angle is kind of gradual, but as the replacement crawls up below the knee and then above the knee, you can see a change in the behavior of the hip angle. And you can see here the foot is the knee is unable to flex during the stance method, and also since the foot is usually not articulated for very cheap prosthesis, you also have a worse problem with the foot angle. So you can see here the foot is really not flexing all that much, and it's kind of like you are forced to do a different kind of gait because there is not really a lot of articulation down your fake foot or your false foot. And of course you have your knee, which is kind of like, okay, so there's some there is some simulation, or at least there is some lifelikeness to the swing phase, but during the stance there is that is where a lot of the problem comes in. So there most of the time it's extended during the stance phase, and that causes compensation on your hip. So yeah, depending on the amount of leg that is replaced, the remaining natural parts of your body have to compensate for the loss of articulation. Even though you have a false knee or a false foot, there is uh, some change in the behavior of your hip. So that's why when you want to develop more advanced prosthesis, you want to make sure that these angles can be achieved by your prosthesis. If not match exactly, at least give them the semblance of it. Like approach at least that level of articulation. So that is it for humans. We're just gonna dilly dally a bit into animal walking gaits, especially four-legged animals. So for horse gaits, actually the interesting part of this is that they walk differently. They have a lot of different gaits available. So we won't be looking at each and every one of them. So for example, you have your walk. So the walk is kind of a slow four-beat gait. If you want the horse to move a little faster but not run, we have what we call the trot. So if you can see here, you have a diagonal gait. So the opposites and the hind and the front legs are contacting at the same time. You also have what we call the canter, which is kind of an asymmetrical three-beat gait, which is kind of unusual, but yeah, it is what it is. And the fastest gait of the horse is what we call the gallop. So you can see here, the horse is essentially flying. These are the footprints of the horse, and you can see that it's just okay, disappears immediately. Yeah, the horse is essentially flying in this case. So again, each of these gaits has a speed wherein they expend the least energy, and the horse picks the gait wherein it will save a lot of energy. So if it wants to walk slowly, it uses the walk gait. If it wants to run really fast, it uses the gallop. So yeah, walking expends the least energy at very low speeds, and the gallop is the most energy efficient when it's moving at high speeds. And these are just the weird rap weird classifications of gait for the horse. So I believe if you own horses, if you're that rich, or if you're part of the stable crew, you can kind of distinguish like these gaits are very clear to you. But for example, for myself, I am not a gait expert in equestrian science, so I am not sure. I'm not able to distinguish these gaits as easily as the experts. So those are the horse gaits. For the canine gaits, they do have a similar kind of variety in the number of gaits that they can assume. But one thing that distinguishes canines and felines actually from horses is that their spine is more flexible. So if you can see here, the gallop of the dog has a lot more flexing of the spine involved. So if we go back to our horse gallop, you can see that the spine of the horse is not moving a lot. The spine of the horse is kind of similar to our spine. It doesn't really move much during running, but for the dog, it is flexing a lot, and this helps with a greater stride, and this helps the dog essentially travel faster for the same amount of flex of the leg. So also their radio ulnar joints, their four leg joints do function. So for the horse, the problem with the horse is that this their their foreleg is essentially kind of very stiff. And that stiffness is actually an adaptation for endurance running. But for the dog, they retain some of this functionality. So they are able to turn very quickly, even though they're running really fast. Also, they are able to feel the foot a little more. So if you recall, the dog usually has four toes on the ground. The horse has kind of sacrificed their toes. They only have one left. And this helps towards energy efficiency during running. But yeah, they kind of feel the ground a little less. And this is advantageous for dogs, especially because they are in the predator niche in ecosystem. So wolves, that includes also felines like cheetahs, like lions, tigers. This kind of helps them be able to respond to the ground. Essentially, they tend to hunt in different environments, and of course, when you're chasing prey like horses or antelope or gazelles, it pays to have a bit more agility when you're chasing down prey. So yeah, and that is it for Gait Biomechanics. Unfortunately, yeah, we do not have the luxury of meeting face to face, or at least we might get memoed if we meet for activities that are not really necessary to conduct online. But yeah, I wish we did conduct this in person. So aside from that, I hope you're having a great day. Next week, hopefully, we'll be able to meet and we'll be able to discuss further kinds of animal motions, because aside from walking and running, animals can do a lot more than just that. So with that, I hope you have a great day and thank you so much.